James Webb just found something at the edge of the observable universe that shouldn't be possible, and astronomers still don't have a clean explanation for it, not a fringe theory. Not a single outlier image misread by an overexcited blogger. A pattern showing up again and again across multiple independent observations published in peer-reviewed journals, forcing working cosmologists to openly question whether one of the foundational models of how the universe formed actually holds up. No exaggeration required. The real data is strange enough on its own. Let's walk through exactly what Webb found, why it's causing this much trouble, what scientists currently think might be going on, and what it would actually mean if the leading explanations turn out to be right. Start with the basic problem, since everything else builds from it. Cosmologists have a working model for how the universe evolved after the Big Bang, generally called lambda CDM, standing for lambda cold dark matter. It's the model that's underpinned most of modern cosmology for decades, describing how gas clouds should have collapsed into the first stars, how those stars should have clustered into early galaxies, and roughly how long that entire process should have taken. Lambda's CDM makes specific, testable predictions about how big and how bright galaxies should be able to get within the first few hundred million years after the universe began. James Webb was built in part specifically to test those predictions, since its infrared instruments can see further back in time and further out in space than any telescope that came before it. Because light takes time to travel, looking at extremely distant objects means looking at extremely early moments in the universe's history. A galaxy whose light left it 13 billion years ago is being observed exactly as it looked 13 billion years ago, essentially a snapshot frozen in transit. Webb's entire scientific mission depends on this fact, using distance as a direct window into the deep past. What Webb found, almost immediately after beginning science operations, was a category of galaxies that researchers have started informally calling impossible galaxies. And the name isn't just a catchy headline invention, it reflects a genuine and ongoing challenge within the field. Within the first year of operations, Webb identified galaxies that had formed within roughly 300 to 500 million years after the Big Bang, and those galaxies were far larger, more structured, and more massive than the standard cosmological model predicted should be possible at that point in cosmic history. These weren't small, faint smudges consistent with early primitive star formation. They were bright, compact, and already showing signs of significant internal structure. The kind of features astronomers expected to see only much later, once galaxies had billions of years, not a few hundred million, to grow and organize themselves. To understand why that's such a problem, it helps to think about galaxy formation the way you'd think about any process that takes time to unfold. Gas clouds need to collapse under gravity to form stars. Those stars need to cluster together and interact to form the beginnings of a galaxy. The galaxy needs time to accumulate more mass, more structure, more complexity. Lambda CDM makes reasonably specific predictions about how fast that process can happen, based on how much matter existed early on and how gravity acts on it over time. Finding fully formed, massive, structured galaxies far earlier than that timeline allows is a bit like finding a fully grown oak tree in a forest that, according to every reliable record, was planted as bare soil only a few years ago. Something in the model doesn't match what's actually being observed. This isn't a one-time anomaly either, which is part of why it's being taken so seriously within the field. The same basic pattern keeps showing up across independent studies using different methods and different targets. In one striking case, astronomers using Webb data identified what they nicknamed red monster galaxies, 3 ultramassive galaxies nearly as massive as the Milky Way, already fully in place within the first billion years after the Big Bang. For comparison, our own galaxy took billions of years longer than that to reach anything close to its current mass and structure. Finding galaxies of similar scale that early in cosmic history runs directly against what the standard model predicts should have been achievable in that amount of time. More recent findings from 2026 specifically have added even more weight to the pattern rather than resolving it. Researchers using Webb identified a massive galaxy formed less than 2 billion years after the Big Bang that appears to have essentially no rotation at all. That's a genuinely strange trait for a galaxy that young. Rotation in galaxies typically develops as a natural consequence of how they form and accumulate mass over long stretches of time. And it's a feature usually associated with much older, more evolved galactic structures. Not something expected in a galaxy still relatively close, in cosmic terms, to the beginning of everything. Finding a young galaxy already behaving like an old one raises the same fundamental question as the impossible galaxies problem. How did it get this mature this fast? Separately, a team at Texas A&M University used Webb to identify an ongoing merger event involving at least 5 galaxies, occurring roughly 800 million years after the Big Bang. That alone would be notable, since complex multi-galaxy mergers of that scale were generally expected to become common well over a billion years after the Big Bang, not before it. But the more surprising part of the discovery involved what the merger was doing to its surroundings. The researchers found gas containing ionized oxygen and hydrogen sitting outside the galaxies involved in the collision. Elements like oxygen are only produced inside stars through nuclear fusion, and only end up outside a galaxy once something, typically a violent event like a merger or a series of supernovae, physically redistributes them into the surrounding space. Finding that kind of chemical enrichment and redistribution occurring less than 1 billion years into the universe's history suggests that complex galactic interactions and the chemical processes tied to them were already well underway far earlier than existing models anticipated. The study's authors published their findings in Nature Astronomy in January 2026, describing a universe that was, in their words, far more complex far earlier than astronomers had long assumed. Put all of these findings together and a consistent picture starts to emerge, not of one anomalous observation, but of a genuine pattern spanning multiple independent research efforts. Galaxies that are too big, galaxies that are too structured, galaxies that are too chemically mature, galaxies that are already behaving, in terms of rotation and internal organization, like objects that should have needed billions more years to reach that state. Each individual finding could plausibly be dismissed as an unusual outlier if it stood alone. Taken together across different research teams, using different methods and targeting different regions of the sky, the pattern is much harder to wave away. So what's actually going on? Scientists currently have a handful of leading explanations, and it's worth being clear that none of them have been definitively proven yet. This remains an active, unresolved area of research, not a settled question with a single accepted answer. One possibility is that stars simply formed faster in the early universe than current models allow. Under this explanation, the underlying physics of star formation itself might need adjustment, perhaps involving more efficient conversion of gas into stars under early universe conditions than researchers previously accounted for. If early star formation was significantly more efficient than assumed, galaxies could plausibly reach larger masses and more developed structures much faster than lambda CDM currently predicts, without requiring any change to the broader cosmological framework itself. A second possibility is that dark matter played a larger or different role in early galaxy formation than current models assume. Dark matter, which doesn't emit or absorb light but exerts gravitational influence, is thought to have played a crucial role in pulling ordinary matter together into the first galactic structures. If the distribution or behavior of dark matter in the early universe differs from what current models assume, that could accelerate the timeline for galaxy formation in ways that would help explain what Webb is observing, again without necessarily requiring a full overhaul of the standard cosmological model. A third, more dramatic possibility is that some aspect of the standard cosmological model itself requires genuine revision, not just a tweak to star formation efficiency or dark matter behavior, but a more fundamental change to how researchers understand the early universe's structure and evolution. This is the most significant possibility on the table, since lambda CDM has been remarkably successful at explaining a huge range of other cosmological observations over the past several decades. Any meaningful revision to it would ripple outward into many other areas of astrophysics, not just early galaxy formation specifically. Researchers are actively working through all three possibilities, along with various combinations and refinements of each. And it's genuinely too early to say which explanation, or which combination of explanations, will ultimately hold up as more data accumulates. That uncertainty isn't a weakness in the science, it's simply an honest reflection of where an active, unresolved research question currently stands. Science doesn't move in a straight line from a single observation to a single tidy answer. It moves through exactly this kind of period, where an accumulating body of evidence forces a field to seriously reconsider assumptions that had previously seemed solid, without yet knowing precisely where that reconsideration will land. It's worth pausing here to address a common misunderstanding that tends to creep into how stories like this get discussed. Finding galaxies that don't match current predictions doesn't mean the universe itself is broken, dangerous, or behaving erratically. The universe is doing exactly what it's always done, existing and evolving according to whatever physical laws actually govern it. What's being challenged isn't the universe. It's a specific human model built to describe and predict the universe's behavior based on the best available evidence at the time that model was developed. Models get revised constantly across every field of science as new evidence accumulates. And a model needing revision is a sign that science is working correctly, not a sign that something has gone wrong with reality itself. That distinction matters, because it's easy for a story like this to get flattened into something sounding more alarming than the underlying science actually supports. Nothing about impossible galaxies threatens Earth, threatens the stability of our own galaxy, or has any near-term practical implication for anyone's daily life. It's a genuinely fascinating puzzle about the deep past of the cosmos, one with real stakes for how physicists understand the universe's history. but it isn't a warning sign about anything happening now or anything likely to happen soon. At the same time, it's fair to say this represents one of the more significant scientific challenges to emerge from Webb's operations so far, precisely because of how foundational lambda CDM has been to modern cosmology. This is a model that's successfully explained an enormous range of separate observations, from the large-scale structure of the universe to the cosmic microwave background radiation left over from the Big Bang itself. A model with that track record doesn't get seriously questioned lightly, and the fact that a respected chunk of the astrophysics community is now treating this as a genuine open problem, rather than dismissing it as observational error or a minor anomaly, says something about how solid the underlying data actually is. Worth noting, too, this isn't the only area where Webb has produced results that surprised the scientists who built the telescope in the first place. Separate research using Webb has found that dust production in the early universe followed more diverse pathways than previously understood, with researchers studying a chemically primitive nearby dwarf galaxy, identifying dust formation processes beyond the traditional explanation involving supernova explosions. None of that specific finding directly ties into the impossible galaxies problem, but it reflects a broader pattern running through Webb's operations generally. A telescope built to test and refine existing models, instead repeatedly turning up evidence that the early universe behaved in ways more complex and less predictable than those models assumed. It's also worth understanding a bit about why Webb specifically is capable of generating this kind of challenge to established theory in the first place, rather than a different telescope doing so. Webb's primary advantage over previous space telescopes lies in its ability to observe in infrared wavelengths with far greater sensitivity and resolution than anything that came before it. As light from extremely distant, extremely old objects travels across billions of light years, the expansion of the universe stretches that light's wavelength, shifting it toward the infrared part of the spectrum, a phenomenon called redshift. Earlier telescopes, including Hubble, could observe some of this infrared light, but Webb's much larger mirror and more advanced infrared instruments allow it to see fainter, more distant, and more redshifted objects with far greater clarity. That capability is precisely what allows Webb to probe the specific era within the first few hundred million years after the Big Bang, where these impossible galaxies are being found. Earlier telescopes simply couldn't see clearly enough into that period to identify these objects at all, which is part of why this particular challenge to cosmological models has emerged specifically now in the Webb era, rather than decades earlier. Launched on Christmas Day 2021 and beginning science operations in mid-2022, Webb was originally designed with a fuel-based mission lifetime of roughly 10 years. Because the precision of its launch trajectory required less fuel correction than engineers had planned for, current estimates suggest Webb actually has enough fuel remaining to continue operating for 20 years or more, potentially extending its scientific mission into the late 2030s. That extended timeline matters directly for this story, since resolving the impossible galaxies problem will likely require years of additional observation, more data points, more independent confirmation across different regions of the sky, and continued refinement of the theoretical models attempting to explain what's being found. A telescope capable of operating for another decade or more gives the field considerably more room to gather the evidence needed to actually settle this question, rather than being left with a handful of early, tantalizing, but ultimately inconclusive results. For now, the honest state of the science is this: multiple independent observations, published through peer-reviewed research and confirmed across different teams and methods, show galaxies in the early universe that are more massive, more structured, more chemically complex, and in some cases more dynamically mature than the standard cosmological model predicts should be possible at that point in cosmic history. Researchers have several plausible explanations on the table, ranging from more efficient early star formation to a different role for dark matter to a potentially more fundamental revision of the standard model itself, but no single explanation has yet been confirmed as the correct one. This remains genuinely open, actively studied territory, not a settled mystery with a tidy resolution already in hand. What makes this worth paying attention to, even for people who don't follow astrophysics closely, is what it represents about how science actually functions when it's working well. A powerful new instrument gets built specifically to test existing theories. It starts generating data. Some of that data doesn't fit the existing predictions. Rather than forcing the data to match the theory, researchers across the field openly acknowledge the mismatch, propose competing explanations, and set about gathering more evidence to figure out which explanation, if any, actually holds up. That process, uncomfortable and uncertain as it can feel in the moment, is exactly how scientific understanding advances over time. Webb didn't break the universe. It found a gap between what a well-established model predicted and what reality actually looks like, and that gap is now driving one of the more significant open questions in modern cosmology. If there's a single thread connecting everything Webb has found so far in this area, it's that the early universe appears to have been busier, more structured, and more chemically active than nearly anyone expected going into this mission. Galaxies grew faster. Mergers happened earlier. Elements got distributed sooner. Structures formed that current models say shouldn't have had time to exist yet. Whether the eventual explanation turns out to be a refinement of star formation physics, a deeper understanding of dark matter's early role, or something more fundamentally new about how the universe's structure came together, the underlying takeaway is the same either way. There's more left to learn about the earliest chapters of cosmic history than the standard model, as currently built, is fully able to explain, and Webb is the instrument currently forcing that reckoning into the open. Sources: Texas A&M University and Nature Astronomy. James Webb Space Telescope finds an early universe-galaxy collision. No One Expected, published January 29, 2026, detailing the discovery of a 5-galaxy merger roughly 800 million years after the Big Bang, along with evidence of chemical enrichment outside the merging galaxies. Science Daily and University of California, Davis, Webb Space. Telescope finds a giant galaxy that does not spin, published May 2026, describing a massive, non-rotating galaxy found less than 2 billion years after the Big Bang. The Astro Manual, James Webb Space Telescope Discoveries 2026, latest images and breakthrough findings, published February 2026, summarizing Webb's findings of ultra-bright, compact, unexpectedly massive galaxies within the first billion years after the Big Bang. Ordupur Narrativa blog, James Webb Space Telescope, Greatest Discoveries of 2026, published June 2026, detailing the impossible galaxies problem and its challenge to the standard lambda CDM cosmological model, along with background on the red monster galaxies identified in earlier research. NASA Science, NASA Webb finds early universe. Analog's Unexpected Talent for Making Dust, published January 2026, describing diverse and unexpected dust formation pathways identified in a nearby chemically primitive dwarf galaxy used as an analog for early universe conditions. It's worth adding some context about how astronomers actually determine that a galaxy is as old, as far away, and as massive as these studies claim, since none of this rests on a simple visual impression from a pretty image. Distance and age, in this context, are established primarily through redshift measurements. As light travels across the expanding universe, its wavelength stretches, shifting toward the red end of the spectrum, and the degree of that shift correlates directly with how far the light has traveled and, by extension, how long ago it left its source. Astronomers measure this shift using spectroscopy, essentially breaking the incoming light down into its component wavelengths and comparing the pattern against known reference points, such as the specific wavelengths at which hydrogen and other elements are known to absorb or emit light. A large redshift value means an object is extremely far away, and given the finite speed of light, extremely old in terms of when its light was emitted. Mass and structure are estimated somewhat differently, generally through a combination of the object's brightness, its size on the sky, and models of how much light a given amount of stellar mass should produce. Researchers compare the observed brightness and spectral characteristics of a distant galaxy against models describing how much mass would be required to produce that brightness pattern, factoring in assumptions about the types of stars present and how much of the light might be obscured by dust. None of these measurements are perfect, and there's ongoing scientific debate about exactly how much uncertainty exists in some of the mass estimates for these earliest galaxies. But the redshift measurements themselves, which establish how early these galaxies existed, are considered quite robust, since they rely on well-understood atomic physics, rather than more model-dependent assumptions about stellar populations. That distinction matters for understanding just how seriously to take the impossible galaxies problem. Skeptics of the more dramatic interpretations have pointed out that some of the earliest, most eye-catching mass estimates for these galaxies came with fairly wide uncertainty ranges, and a handful of initially startling results have been revised downward somewhat as more detailed follow-up observations came in. That's a normal and healthy part of the scientific process, not a sign that the entire phenomenon is illusory. Even accounting for that normal downward revision in some individual cases, the broader pattern across dozens of separate galaxy candidates, studied by multiple independent teams, has held up well enough that the core puzzle remains firmly on the table, rather than being explained away entirely. It's also worth situating this discovery within a slightly longer running tension in cosmology that predates Webb entirely. For years, before Webb launched, astronomers had already been wrestling with something called the Hubble tension, a persistent mismatch between two different methods of measuring how fast the universe is currently expanding. One method relies on observations of the early universe, derived from the cosmic microwave background radiation. The other relies on more direct local measurements of nearby stars and galaxies. The two methods consistently produce slightly different values for the universe's expansion rate, a discrepancy that has resisted a clean resolution for over a decade, despite significant effort from multiple research groups using increasingly precise instruments and techniques. The impossible galaxies problem isn't the same issue as the Hubble tension, but the two sit within the same broader category of open questions, places where increasingly precise observations are producing results that don't cleanly fit within the standard cosmological model as currently constructed. Some researchers have speculated that a more fundamental revision to the standard model, one capable of addressing several of these open tensions simultaneously, might eventually emerge from continued work in this area. Others believe the issues are more likely to be resolved individually through refinements to specific pieces of the existing framework rather than a wholesale replacement of it. Which camp turns out to be right remains, again, an open and actively debated question within the field. None of this uncertainty should be mistaken for the field being in disarray. Cosmology as a whole rests on an enormous body of successfully tested predictions, and Lambda CDM remains even now the most successful and widely accepted framework available for describing the universe's large-scale structure and history. What Webb has done is sharpen a specific edge of that framework, the very earliest chapter of galaxy formation, revealing that this particular corner of the model needs more careful attention than previously assumed. That's a meaningfully different situation than the field being thrown into chaos, even though headlines sometimes frame it that way for effect. For anyone wanting to actually follow how this story develops, rather than just reading a single snapshot of where things currently stand, a few practical signposts are worth watching. Continued spectroscopic follow-up on the specific impossible galaxy candidates already identified will help narrow down the uncertainty in their mass estimates, potentially confirming or revising the most extreme cases. Additional discoveries of similar objects across different regions of the sky studied by different research teams will help establish whether this is a widespread phenomenon or concentrated in a smaller number of unusually extreme cases. And thus, theoretical work modeling alternative explanations, whether involving revised star formation efficiency, different assumptions about dark matter, or more fundamental changes to the cosmological model, will gradually narrow down which explanations remain viable as more data accumulates and rules out the weaker candidates. It's a genuinely exciting time to be following this particular corner of astrophysics, precisely because the outcome isn't predetermined. This is one of the relatively rare moments in modern cosmology where a well-established, decades-old framework is being seriously tested by new data, in full public view, with the scientific community actively working through competing hypotheses rather than defending a single settled position. Whatever the eventual resolution turns out to be, the process itself, a powerful new instrument generating data that doesn't fit the prevailing model, followed by open scientific debate over what that mismatch actually means, is a genuinely healthy and valuable one, even when it produces headlines that sound more alarming than the underlying science actually warrants. There's one more piece of this worth walking through before pulling everything together, since it's a question that comes up constantly whenever this topic gets discussed outside of specialist circles. If the standard cosmological model turns out to need real revision because of what Webb has found, what would that actually change, practically speaking, for anyone who isn't a professional astrophysicist? The honest answer is, in the near term, very little in terms of daily life. This isn't a discovery that affects weather prediction, GPS accuracy, medical technology, or anything else with immediate practical application. What it affects is our collective understanding of where everything, including us, ultimately came from, and how the universe's earliest chapters actually unfolded. That might sound like a purely abstract concern, but it's worth remembering that fundamental physics discoveries have a long history of eventually producing practical applications that weren't obvious at the time they were made. Understanding of atomic structure, developed initially out of pure scientific curiosity about how matter works, eventually led to nuclear power and medical imaging technology. Understanding of electromagnetism, developed through theoretical physics research with no immediate practical goal in mind, eventually underpinned the entire electronics industry. None of that means a revision to early universe cosmology will necessarily produce a comparable practical breakthrough, and it would be irresponsible to promise anything like that. But history does suggest that dismissing fundamental physics research as purely academic with no eventual real-world relevance has repeatedly turned out to be a mistake over the long run. More immediately, though, the real value of this research isn't practical application at all. It's simply a more accurate picture of reality. Understanding how galaxies actually formed, how fast structure emerged from the early universe's initial near-uniform state, and what physical processes govern that transformation is valuable on its own terms, as basic knowledge about the universe we all live in. Not every worthwhile scientific pursuit needs to justify itself through eventual technological payoff. Sometimes, the honest, complete answer to why this matters is simply that it's genuinely fascinating to understand more accurately how everything around us came to exist, and Webb is currently providing humanity's clearest look yet at that specific foundational chapter of cosmic history. It's also worth acknowledging, in the interest of giving a complete picture, that not every astrophysicist agrees on how significant this challenge ultimately is. A meaningful portion of the research community views the impossible galaxies findings as a genuinely serious anomaly requiring real theoretical revision. Another portion views it as likely resolvable through more modest refinements to existing models, particularly around star formation efficiency, without requiring a fundamental overhaul of the broader cosmological framework. This kind of disagreement, playing out through competing papers, conference presentations, and ongoing peer review, is exactly how contested scientific questions get resolved over time, through sustained evidence-based debate rather than a single authoritative pronouncement settling the matter immediately. Anyone encountering confident, definitive claims in either direction, that the standard model is definitely broken, or that there's definitely nothing to see here, should treat that confidence with some skepticism, since the honest state of the field right now sits somewhere in the genuinely uncertain middle. Bringing this all together, the version of this story worth actually paying attention to isn't a doomsday framing about the universe being fundamentally wrong or broken. It's a more grounded, more interesting story about a powerful new scientific instrument doing exactly what it was built to do, testing a well-established model against new, higher quality data, and turning up results that don't cleanly fit. That mismatch has sparked a genuine, ongoing scientific debate, involving some of the most capable researchers in the field, with multiple plausible explanations still on the table and no single answer yet confirmed. It's early, it's unresolved, and it's one of the more compelling open questions in modern astrophysics, precisely because nobody, including the scientists closest to the data, can say with full confidence yet exactly how it's going to be resolved. That uncertainty is exactly what makes this worth following, rather than dismissing as either overhyped or fully settled. Keep an eye on new peer-reviewed papers over the next couple of years, since that's realistically the timescale on which a clearer picture is likely to emerge. Webb still has well over a decade of fuel left, the relevant research teams are actively collecting more data right now, and the specific question of how the earliest galaxies grew so big so fast is, for the moment, still genuinely open. Whatever the eventual answer turns out to be, it's going to come from exactly this kind of patient, evidence-driven process, not from a single dramatic announcement settling everything overnight. And that slower, more careful path is ultimately what makes the final answer, whenever it arrives, actually worth trusting. That's the real story sitting behind a headline like this one, stranger and more honest than any invented drama could be, and it's still unfolding right now, one careful observation at a time.